We've seen in earlier videos that kinematics can be applied to rotational motion, and now we'll show that dynamics can be applied to rotational motion. And what that means is we have to think about force, but force when we are in a rotational motion is actually torque. And so we'll go back to the idea of torque now. Okay, so let's add some force to this, right? So Newton's law tells us that a net force will result in a net acceleration, right? That's just F equals ma. We know that. So we want to accelerate this toy plane, right? And we know we want to accelerate it in the tangential direction, okay? And we can really think about this almost as just a linear problem, right? We want to accelerate it in this direction, okay? And so we need to apply a force in that direction. And that force and that acceleration are going to be related by the mass of the plane. But if we think of this whole thing together, right? And think of this as a kind of string plane system with this little boy at the middle of it, we can see that that requires a torque. Okay, why do we know that? Well, because we've got a force and we have a lever arm. Okay, and so this, if we thought of that less as a string and maybe as a stick, you can imagine that the force, if that stick, as we can consider that stick massless, the boy is trying to turn the plane that way by applying a torque to his stick. Okay, so let's multiply both sides by r cosine theta. And the reason we want to do that is so that we end up with, here is our definition of torque, right? Force times lever arm, perpendicular lever arm, cosine theta. And then we're adding an r to this side too, so we've added that r. So we can restate this as torque, so this side is our torque, is going to be equal to mass times tangential acceleration times r times the cosine of 90, which is just going to be 1. Okay, and then we're going to sub in a definition for tangential acceleration that has to do with rotational motion. So this is from last time. We just know that the tangential acceleration is the angular acceleration times r. And so we're plugging those in here. This guy goes away. This guy gets subbed out as this. And we end up with this equation here. Torque equals mr squared times angular acceleration. Now, this looks a little bit like Newton's law if we use our imagination. If we do that, what are we subbing in here? This becomes our rotational force. This is our rotational acceleration. And this becomes something like our rotational mass. It's equivalent to a mass in a linear problem. And when we solve these problems, we often substitute this guy for I. And I is a really interesting physical characteristic. You can see it has the mass in it, but it also has the radius, right? Because that radius is pretty crucial to how torque works. So what is I? I is called the moment of inertia, and it's essentially the rotational mass. It is the resistance to acceleration when a torque is applied, in the same way that mass is the resistance to acceleration when a force is applied. So the more torque I apply, the more acceleration I'm going to get, right? But if I have a large I and I have the same torque, my acceleration is going to be lower. Just like if I'm pushing a semi-truck with a given amount of force, it's going to accelerate more slowly than if I'm pushing a car with that same force. So our moment of inertia is our rotational mass, essentially. It's our resistance to mass. It's the rotational inertia of this system. Okay, so an object with a high moment of inertia requires more force to accelerate it rotationally, just as an object with a large mass requires more force to accelerate it linearly. So that's the definition of I. how do we actually calculate I? That's quite difficult, actually, in a general way. Here's our formula for that, and this just means the sum of all of our particles of mass multiplied by their radius squared. So if we were going to figure out I for this object, we'd have to find all of the mass points. Here's m2, multiply it by r2 squared, add it to m1 times r1 squared, m3 times r3 squared, and add all those up over the whole object. You can imagine that that's quite difficult for any shape that's not going to be really easy. And so we're not going to actually calculate any moment of inertia. What we do is we go to a bunch of tables, right? And so tables like this allow us to know what an I is based upon someone else's calculations, essentially. Someone has done the calculus to figure out these values. And so, for instance, a solid cylinder here, you're going to have this formula, and that m there is going to be the mass of your object. Your r2, or your r squared, is going to be the radius of that cylinder, and so forth. The simplest version of this is something like a hoop, right? Because all of the points in this hoop, a very skinny hoop, are going to be at a radius r. And so we can take the whole mass times r squared. Okay, anything where the mass is closer, or different distances, is going to be less than this. So this is going to be the kind of maximum for our moment of inertia. Why is that? Because all the points are out here, right? All the mass is far away. If any of the mass is closer, then our moment of inertia is going to be smaller than that. So the big idea here, and this moment of inertia is a little tough to get your head around, but we want to remember that moving mass away from the axis of rotation increases the moment of inertia and makes it more difficult to accelerate the mass. Okay, so let's take two spheres. They have the same radius and they have the same mass. Okay, one is made of aluminum over here and the other is made of gold. So gold is a lot more dense, which is why these can have the same mass even though this one is solid and this one is hollow. So we want to know which one has the greater moment of inertia. Well, the m is going to be the same for both, but the difference is this one has all of that mass far away from our axis of rotation. This one has a bunch of mass that's along the axis of rotation, and so the bigger moment of inertia is going to be the hollow gold one because it has more of its mass far from the axis. That's the big. So if you can get that straight, that if you move your mass away from your axis of rotation, it's going to increase your moment of inertia and increase the difficulty in accelerating the mass, then you have the main idea. Okay, so you have a larger I, and that means for a given torque, your acceleration is going to be lower. If my I is 10 and my torque is 10, my acceleration is going to be 1, right? But if my torque is 10 and my acceleration is 1, then my acceleration is going to be 10 units. Okay? So increasing I lowers your acceleration for a given torque. So what does that energy look like? How do we measure that energy in a rotational motion? If we think about our little boy flying his airplane over here, we can think about the energy contained in this plane. If we imagine our string here, our stick is massless, and we'll be able to find out what the energy in that plane is as it rotates. So we know this is true, right? Ke equals half mv squared. All we're going to do here is sub in tangential velocity here for our v, and we know tangential velocity is equal to r times omega. And when we multiply this out, we end up with an r squared term here, as well as an omega squared term. And that then looks familiar to us too, right? This is our moment of inertia I. And so once again, we find that our equation looks eerily similar to our linear equation, right? So instead of Ke equals half mass times velocity squared, here we have moment of inertia times omega squared, our rotational mass I and our rotational velocity omega. So when we think about this in terms of energy, if we have something that's spinning at the same rate, if it's got a bigger I, then it has more energy, which makes sense, right? Because it took more energy to get it spinning at that same rate because it resisted our rotation a lot more. That term, our rotational kinetic energy, allows us to finish our definition of mechanical energy. So we talked about mechanical energy as our kinetic plus our potential energies. We dealt with two kinds of potential energies, spring and gravitation. And then we had linear kinetic energy, but now we can add rotational kinetic energy here. Okay, so if we wanted to figure out the mechanical energy of, say, a rolling wheel, we would have to think about how high it was, whether it had compressed a spring, how fast it was rotating, and also how fast it was moving in a line. And this is why when we talk about pulley systems, we say that our pulley system is, our pulley is massless, because if it's not massless, as most pulleys are in fact not massless, it's going to require some energy to get that pulley to turn. And so it would change our equation a little bit because we'd have to include the energy that went into actually turning that pulley.